For our last session for this, presentation for this session, I'd like to welcome Simon Whiteley from Whiteley-Safety Engineering Management Limited, and he'll be talking about investigating beyond Swiss cheese and Dominoes, cast accident analysis overview. Thank you very much.
Thank you. My name's Simon Whiteley. I work predominantly in the civil and defence aerospace, so large aircraft, fast jets, helicopters, missiles, air traffic control, but I've also got some experience in defence maritime, defence nuclear with AWE, armoured automotive, healthcare and government IT, rail and pharmaceuticals, and now developing into unmanned air systems, autonomous vehicles and cyber security. I offer training, consulting and coaching in system safety engineering and safety critical project management, but I'm focusing primarily on using the stamp-based safety assessment methods across the whole life cycle, but particularly accident investigation. Now you might be wondering, what is stamp and what is cast in the highlight of my presentation? Well, to address that, I've got three basic objectives for my talk today. The first is I'd like you to open your minds. You know, as the saying goes, minds are like parachutes, they only work if they're open. I'm going to provide a very brief overview. There's not much time to go through. I've got a lot to get through, so this is going to be very brief, quite a pace. But I also want to inspire you and plant a seed in your mind so that after this presentation, you go of your own free will and go and investigate, learn about stamp and the various other methods I'm going to talk about today. So just a bit of context then, before I tell you what stamp and what cast is. So hands up who's familiar with the diffusion of innovation curve. Is this concept familiar to anybody at all? No, there's literally nobody. Okay, right. Essentially, this is the theory of how, why, and how fast new ideas or new technology spread. So you might be familiar with the original iPhone introduction in 2007, new idea. So at the very early stages of a new innovation, you have innovators, pioneers, risk takers, trendsetters, who want to try something new, take the risk and see what advantage they can get. And then over time that transitions into more people as early adopters, the early majority, the late majority, and then finally the laggards at the back. Now they may not be able to take on the new opportunity because they're not required to by regulations, or they just don't want to take the risk, they don't like change. Now stamp is essentially very much in that early innovator stage. It's been around sort of on and off since the late 90s, early 2000s, but it's only really in the last 5 years where it started to get traction and get interest from various industries. Now, its usage is predominantly in private, behind closed doors, so there aren't many private companies or governments talking about this, and there's two main reasons for that really. The first is that if you use these approaches, the stamp-based approaches, because of their nature and their power, you might find things that you either weren't aware of or that you don't really want to speak about in public. So they don't really talk about it. The second reason is the competitive advantage that these processes can give you, especially if you apply them in the early design stages and early stages of perhaps concept. And we've talked a little bit about that this morning already. Now, being a system safety engineer across a number of industries and domains and having challenges with safety cases and probabilistic assessments and fault trees and all that kind of stuff, as part of some of the work I did, I found that those tools and techniques were somewhat limited in the problems I was trying to address, and we've spoken about some of those limitations this morning. And so when I first learned about stamp, I saw the opportunity that it could provide to my clients and customers, and so I set out on a bit of a personal mission to help people understand that, move it out of academia into the mainstream, and then help organisations, reduce risks, save lives and save a bit of money as well. So I'm essentially trying to move the stamp approach out of academia and get it into the hands of more and more people. Now you may or may not know, I've run a number of webinars over the last couple of years, since about 2016, and as part of those webinars teaching people about stamp, I've had interest from over 22 different countries from across the globe, over 17 different industries and domains, and those industries and domains I've highlighted in green, they're the ones that are really starting to see the benefit to this and taking advantage of it and starting to use it and get experience. So now, what is stamp and why do we need it? Well, some of the challenges. Hands up who's familiar with this accident. So this is the Uber autonomous vehicle accident from March 2018, last year. And it was touted as the first fatality due to autonomous vehicles. We've already talked about autonomous vehicles already today. Now what's interesting about this accident is that the lady that was hit by the vehicle was detected by the vehicle. The vehicle knew the lady was there, but it didn't activate the brakes. And it did that because it was programmed and designed to do exactly that. So there was no technical failures in this situation. And so if we're using safety assessment approaches that are focused on failures, then this particular accident wouldn't feature in that type of safety assessment. Now the challenges I've highlighted here are becoming more and more prevalent, and you'll recognise some of these, I'm sure. So the speed of technical innovation and the need to be first, especially in autonomous vehicles. Complexity, challenges with complexity, as especially software. Connectivity, interdependency and interactions. There's a mention earlier on about human role changes, so from doing the work to being a supervisor of automation that's doing the work. And the concept of human errors being symptoms as opposed to causes. And also the change in the nature of certain accidents from being due to failures but now due to more unsafe interactions, so not failures. So then we get into what's STAMP. So STAMP primarily is an acronym, as I'm sure you guessed, and it stands for Systems, Theoretic, Accident, Model and Processes. And it originates from a professor at MIT in the US called Professor Nancy Leveson. Can I have a show of hands if you know her name? Read any of her papers? Oh great, excellent, that's better than the last question. Okay, so Nancy, in her second book, Engineering a Safer World, she introduced the concept of STAMP and the safety assessment processes based upon it, and she's kindly made available that book as a free PDF download. So if you go on the MIT Press website or search on Google, you can download a caution of that and learn about it yourself. STAMP, as I mentioned, it's an acronym and it refers to two parts. It is what's called an accident causality model or foundation, and then a set of processes, analysis and design processes based upon that accident causality model. Now that model is based very much on systems thinking, systems theory and control theory concepts, which is the same basis principles that we have in systems engineering that I'm sure most of you are familiar with. So when we talk about accident causality, and this has been a thread throughout all of the conversations this morning so far, so when I talk about an accident causality model, I'm referring to a model or paradigm or belief about how things happen or could happen, causality. And it underpins efforts to think about, discuss, manage and engineer for safety, but also in the context of this presentation, it underpins how you might do an accident or event investigation. And it's often not explicit or documented. Literally everybody in this room has an accident causality model in their mind, whether they realise it or not. And you know, in terms of a mental model, that's part of your being as an individual, as a person. Hands up who's familiar with this accident causality model. So everyone should know this one. Great. So this is the world famous Professor James Reason's Swiss cheese model. The general principles are to protect your assets and your people from hazards. You put in some layers of defences in depth, and the principle is that so long as you maintain those defences, then you should not have any accidents and everyone can go home happy. Now unfortunately the real world's more complex than that, and you do get holes in those defences, and essentially the efforts to prevent accidents involve understanding where those holes are and trying to ensure that the holes don't line up. Hands up who's familiar with this one. So this is the Heinrich's Domino Model. So same sort of principles, linear progression from cause to effect. If you remove one of the dominoes, you prevent the progression to an accident, and everyone should be fine, everyone should be safe. Hands up who's familiar with bow ties. Excellent. So this is just another example of the same principles of linear accident causation. And this is where we get into what STAMP is all about, what makes STAMP different and broader. So on the left-hand side, I talk about the traditional view, so Swiss cheese, dominoes and bow ties. And the general principle is that accidents are chains of directly related events or due to breached barriers. And it essentially defines safety as a management of failures problem. So preventing accidents is essentially managing and preventing failures and the consequences of failures. Now the STAMP accident causality view is essentially the realm of what are called control loops and structures. And essentially accidents involve complex dynamic processes, and it defines safety instead of management of failures. it talks about dynamic control problem. So it includes failures like the traditional approaches, but it also includes circumstances that are not failures but will result in an accident, and that's really what makes it more powerful. And essentially, to prevent accidents in the stamp-based approach, you enforce what are called constraints on system behaviour and interactions amongst system components using what's called a control structure. And you'll notice I use square brackets a lot, and what I'm trying to do by putting square brackets in the presentation is they're English words, terms that you probably use every day, but I'm using them in a very specific context with a specific definition. So when you see the square brackets, just think Simon's being specific here. Okay, so hands up how familiar this is. This is just a standard basic closed loop, feedback loop control. There's a few confused. Yep, excellent, great, everyone's awake. So essentially the principle under STAMP is to enforce safety constraints on your system, your process, to prevent hazards resulting in accidents. And we do that through these control loops. So in principle, we have a control process that has a controller controlling it, and that controller influences that process through what's called control actions, and they could take the form of anything dependent upon the specific system you're looking at. Now those control actions, if they can result in an accident, then they are labelled unsafe control actions. Now when we're talking about an accident investigation, we don't normally say things are unsafe actions because that introduces judgmental language, particularly on the behaviour of humans, that if they've perished, they're not able to defend themselves and explain why they took the actions they did. So we talk about these as in the context of contributory control actions. Now, there are essentially 4 contributory control actions, and these might sound familiar to you if you do functional hazard analysis or functional failure analysis. So the first is a control action required for safety is not provided. The second is an unsafe control action is provided, and that results in an accident. The third is associated with timing, so if the control action is too early, too late, or in the wrong sequence. And then the final one, the fourth one, is about the duration that control action is provided, so if it's provided too long or too short. Now I'm sure these are all quite familiar to you already. Okay. So once we've thought about these control actions and which ones result in accidents, we then start to think, well, how can these unsafe control actions occur? And essentially we look around the control loop and look at issues with the controller itself, perhaps. We talked earlier on about seismic events. We can talk about control algorithms. Now, control algorithm is just a technical term to refer to the thing that defines the behaviour of the controller. So if it was you driving your car, the way that you've driven your cars for years and the way that you were taught, you've got an inbuilt control algorithm in how to operate your car. And if you go from a manual car to an automatic car or the other way around, you'll notice, when you go to press the clutch, you end up through the windscreen. That's because your control algorithm is inappropriate for that particular circumstance. Then you have what's called the concept of a process model, and that essentially is a model of what's happening in the control process. And if you're a human, if this is a human controller, that would be one of your mental models. And they are updated by feedback about the control process, and ultimately that is, that's the control feedback loop. Now, when we talk about control structures, this is essentially a representation of lots of these feedback loops arranged in a hierarchy dependent upon the system that you're particularly looking at. So in this case, you could have a chemical process down here or a nuclear process. You've got an automated controller with some actuators and sensors. And above that, hierarchically, you could have a human controller. And above that, you could have the plant management. And essentially what I'm showing you here is this approach using control loops and structures. It allows you to model literally any system you want, whether it's completely technical, whether it's got autonomy, artificial intelligence in it, whether it's purely humans, social technical, the whole shooting match. And it's very flexible in that respect. And this is just an example of a very basic control structure, just to give you an idea of how flexible it is. So if you want to model the operational process, in this case, this is an air traffic control system, so we have an aircraft with its trajectory, we've got some air crew, we've got an air traffic controller, We've got an airport ATC management, airline operator. So this is very much the operational system. And above that, you've got an operations control structure, a maintenance control structure, and then an emergency response control structure, depending on the circumstances. Now, if you want to, you can then also think about the designers, the governmental, legal, and regulatory control structures. And it allows you to think very broadly. But obviously, you don't have to model everything if you don't want to. Now, this chap's probably not that famous, I don't know, but this is George E.P. Box. He's a world famous, apparently, statistician, and he said many things. One was, all models are wrong, but some are useful. So the reason I'm highlighting this is obviously this is a model-based approach. You create a control structure model, so your analysis is based on that. So depending how detailed the model is, will affect the results that you get from it. So what are the stamp-based processes? Well, there are currently 4 stamp-based processes. I'm not going to talk about all these because we don't have too much time. STPA, Systems Theoretic Process Analysis, is a hazard analysis approach that can be used in the design process traditionally earlier than fault trees, FMEAs and everything else. So if you use this approach early, before you've got a design, you could reduce the risks and reduce costs. Then we've got CAST, which I'm going to talk about today. CAST is an acronym as well. It stands for Causal Analysis Based on Systems Theory. And its prime objective is to understand what was that control structure on the day of the accident and understand why it was inadequate, why the control was inadequate, why the safety constraints were not enforced. So now to give you an overview of CAST. So hands up who does investigations. Accident investigations, incident investigations. Okay, great. So this is just a very high-level investigation process. You observe the scene, observe what's gone on. You document the facts, however you document them, and then you do a plan. And that plan essentially is how are we going to investigate it? What technical expertise do we need? You know, in the case of air accident investigation, we might need an engine expert, a human factors expert, you know, an aircraft design expert. So you'll collect some facts, you'll do some analysis, you'll form some findings and conclusions, and then you'll make some recommendations. Now, CAST accident analysis is part of the analysis phase of your investigation. And the better you get with CAST, you could also use it to inform your plan and make decisions about what resources you need to do your investigations. Now, if you want the CAST accident analysis on a 1 page, that's essentially it. So the first thing you do is you define your losses, or accident, you know, what's happened. Then you define the hazards, what are the hazards associated with those losses. Then you define what are called high-level safety constraints, and they are the requirements or constraints that are required to be enforced by the control structure to ensure that the hazards either are not released, or if they are, you can appropriately respond. Then you do some modelling, timeline, create your normal timeline. Then you can create the control structure model, and then the last part is your analysis of that model. And that's in 3 parts: the physical process, the components of the structure, you know, the controllers, and then the structure itself and how that contributed to the accident. And then, of course, make recommendations. Now, it's not a linear process. It is iterative, dependent upon the investigation you're doing, but that is the broad sort of structure of it. So we've not got much time. Let's see how we can get through this. So from an aircraft fan cowl door loss example. So I know it's an aerospace example. I do apologise. So this is an Airbus A319 engine. I think it's a V2500. That probably doesn't mean anything. But what we're focusing on is these what are called fan cowls. So this is the engine fan. These are the fan cowl doors on the outside, and they essentially open from the bottom like a clamshell, so that you can do the servicing on the engine, check the oil levels and all that good stuff. Now on this particular accident aircraft, the aircraft took off with these fan cowl doors on both engines unlatched. So you can see the latches just under there, both engines. These are the latches close up. They're supposed to be painted orange, but if they're not maintained properly, they look like this, so they're not very visible if they're hanging down underneath. The aircraft took off, both fan cowl doors on both engines got ripped off. Fortunately, the left-hand engine wasn't functionally affected, but the right-hand engine developed a fuel leak, a hydraulics leak, and damage to some of the electrical harnesses on the aircraft. The aircraft took off in a westerly direction, flew around London. At the takeoff, that's when the doors detached, that's when the fuel started to leak. But the aircrew didn't know there was a fuel leak until 10 minutes later all the way over here. So they were leaking fuel all across London, And then on approach to the airfield to return, that's when they had the engine fire. So that was, central London we're talking about. And then they finally landed, shut the engine down. Everybody survived, no major issues. So this is just a picture of the engine with some of the damage. You can see the doors, the doors should come all the way across here, and that's all that's left. You can see the fire damage over here. And then this is the reason why the doors were opened. So on that particular occasion, before the aircraft took off, there was some night maintenance performed by a team of 2 maintenance technicians. And they were tasked to maintain various aeroplanes, and this was the second one that they were to maintain. And as part of the maintenance for this aircraft, they were required to open the doors and look almost underneath to check the oil level for the electrical drive generator on the engine. And what they did is they opened the doors, found that they needed some oil, but because they didn't have the tools with them to top the oil up, they decided to leave the doors as they were. They didn't latch them, and then they went off to go and get the tools that they needed. But the tools that they needed were located at a different part of the airfield. So if you're familiar with Heathrow, you've got 2 runways. This is British Airways Terminal 5 with the other terminals. You'll get an idea of how big this place is. So if you're driving a car, it does take a long time to get between some of these places. So they started, there we go, help if I did this. So they started at this aircraft, went to number 2, this was the accident aircraft, then number 3, and then basically round in a circle. And this was during the night, so from like 7 p.m. in the evening to 6 a.m. in the morning, so it was dark, night time. They didn't have the equipment they needed. The equipment that they could have got was basically located all the way over here, so it was very difficult for them to collect that information. So on the way back to this aircraft at the end of the shift, they actually drove straight past the aircraft they should have been working on and started to work on a different aircraft, which, funnily enough, the oil was already topped up and the doors were already locked, which you would think was a bit confusing. But anyway, so returning to the aircraft, this is an example at night time, so same sort of time, same conditions. That's the tail number of the aircraft painted on it, and then again on the front nose, and that's all the visual cues you get from a human factors perspective when you return to the aircraft. But they didn't see those anyway. I mean, you can see the engine in the background. They're not massive aeroplanes, but these visible cues are not that obvious. So the accident itself, the aircraft was damaged. There was fire damage, fuel, hydraulics leaks, loss. There was the potential for multiple deaths, total loss of aircraft, deaths on the ground, injuries on the ground, and damage to assets on the ground. The British Airways share price could be devalued. Negative media coverage, brand damage, so-called second victims. So these are the people involved in the accident that have not been harmed but are psychologically affected by it. And then, of course, a massive busy airport. The airport disruption is significant. Now, before we move on, I just need to make a point here. So I'm sure you've all had endless conversations about what's a hazard. Does that sound like conversations you've had? How do we define hazards? So when we're talking about doing a stamp-based safety assessment, whether it's STPA or CAST, we're using a very specific, constrained definition of a hazard. Now, I'm not going to go into it in the detail now because it's a long conversation, but when somebody tries to compare a traditional safety assessment with a stamp-based assessment, always keep at the back of your mind that it is a different definition, and this definition is very much more constrained around what the designer or operator can actually control. So it's not, a hazard in this context is not literally anything that could cause harm. It's more constrained than that, and I just need to highlight that. So the hazard in this case is the aircraft was released for service in an unsafe condition. I don't know if you can see that from the back, but this is the high-level safety constraint. So the control structure we spoke about shall prevent the release of an aircraft for service in an unsafe condition, and there are 2 more hazards constraints you can break down from that, and that is that the control structure shall ensure the fan cowl doors are closed and secured before flight, and then the second is that those doors remain closed and secured during flight. And you'll notice the subtlety in those 2. One is about the design and humans involved in the process of preparing the aircraft, but the second constraint is purely about the design of the aircraft, keeping those doors closed. So as I said, the ultimate goal of CAST accident analysis is to understand what was the control structure that existed at the time to enforce those safety constraints, and then how and why each level of that control structure allowed or contributed to inadequate control. Now, this is a very high-level control structure for the maintenance. So we've got the aircraft at the bottom, we've got the two maintainers working together, we've got what's called the aircraft technical log that defines what the aircraft has had done to it. We've got the printed work allocation sheet, the aircraft maintenance manual, and then we've got the management of the maintenance activity. British Airways is a maintainer, and then the regulator, the European Aviation Safety Agency, at the very top. Okay, so this is the fan cowl, we've talked about that. So when we analyse the physical loss, we first list the physical equipment. So in this case, it's an Airbus A319, fan cowl doors. We consider physical failures. So you know I said about failures versus non-failures that are dangerous. So this is where your failure analysis is included. So we've got the doors detached and there was inadequate high visibility paint. I'm not going to emphasise why that's important now. In unsafe interactions, so the unsecured doors interacted with high airflow which caused them to detach. The contextual factors is that the doors were not secured. And then we summarise the role of that physical component in the accident. So in this case, the fan cowl doors detached, impacting critical parts of the aircraft. Now there are some unanswered questions, and these are not answered in the investigation report for whatever reason, but it's about the certification, the engineering requirements that are required by the regulator. So in aerospace we have these things called certification specifications, CS, and 25 is related to the large aircraft. Now these particular doors, as required by this regulation, should be able to sustain flight loads. Clearly they didn't because they came off. So why was that regulation violated? Then we've got CS 25-1309. This basically says you shall do a system safety assessment of your design, and that design should include consideration of the doors. For some reason, Airbus did not do that, and it was not established at the time. Then there's some recommendations. So we can make recommendations immediately on certification and safety assessments, and also on structural integrity and crew alerting. And then we get into the analysis of the components. So I'm going to pick these two here because we haven't got time to go around all of it. Now there are essentially three parts to the component analysis. The first is to consider safety requirements and responsibilities, and then the control actions. And then the second is to explain the actions and the behaviours. So we can look at mental models and contextual factors, and then ask any other questions that we need to establish as part of the investigation. So first off, safety-related roles and responsibilities. So the maintainers need to perform daily and weekly checks in accordance with procedures, and then report anomalies to management. In terms of their ability to influence the aircraft, you know, the technicians were fully capable of operating the fan cowl door locks, so there was nobody with a broken arm or anything like that. From a contributory control actions perspective, the technicians did not secure the fan cowl doors, and they returned to the wrong aircraft. From a mental model and process model flaw perspective, we already talked about the fact that they returned to the wrong aircraft. So they were performing the activity but to the wrong aircraft, and they were not aware of that. And when we talk about why that is and what the contextual factors are, we can talk about disrupted activity, because obviously they had 7 different aircraft to work on. They had to move around the airfield, pick up tools and equipment. It was night time. It was quite a disrupted activity. The technical log availability, so the thing that tells the maintainers about the state of the aircraft, was not actually on board the aircraft. For this particular aircraft, on a weekly check, they take the log off the aircraft and put it in the maintenance office away from where they are, so they had no frame of reference. Equipment availability, so they didn't have the oil guns that they needed. Inadequate feedback upon returning to the aircraft, so we talked about the markings on the aircraft, telling them what aircraft it was, and then also fatigue, shift working and overtime. So it was a night shift, these maintainers were doing overtime, you know, there were challenges with scheduling of workers and having enough workers. And then in summary, the technicians did not secure the fan cowl doors. So there's a couple of questions there. You've probably already alluded to these already. The first is, why did the technicians not verify what aircraft they were working on? The second is, why did the technicians not close the loop on who had effectively completed their task? Because I'm sure if you're doing a safety critical task and it's already been done, you'd like to follow up and find out, well, who's finished my job, you know. That wasn't addressed in the investigation. I pressed the wrong button again, sorry. So then we do some structural analysis. So this is beyond just the components themselves. So we talk about the structure, the architecture and interactions. So the technicians began their shift together, but later on in the shift they had to separate into separate vehicles. So when they drove back to the aircraft they thought they were working on, they missed the opportunity to cross-check with each other. The locations of work equipment was very remote from where they were doing the task, and their responsibility for ensuring adequate control of maintenance per aircraft was inadequately allocated and performed. So they were just given a list of aircraft to work on, crack on. They weren't given updates to that list. In terms of communication and coordination across the control structure, you've got multiple teams of technicians, engineers and maintenance managers working all over the airport on different aircraft. So there's no sort of common situational awareness of the safe state of the aircraft. In terms of dynamics and changes or evolution of the control structure, we can talk about the technical log movement from on board the aircraft, changes to the maintenance task list due to aircraft arrivals and delays, unexpected maintenance tasks such as the drive generator needs servicing. So they don't normally need the oil, so they wouldn't carry it with them. It was only on this special occasion that they needed the oil to top up. And then safety management systems. So we can talk about fatigue risk management and how it was or was not managed in this case. We can talk about equipment availability, things that are broken and not reported. Aircraft released to service post-maintenance. So how do they hand over between the maintenance control structure, hey, this is a safe aircraft ready to go, and then the operators, the pilots, yeah, right, let's go flying with the safe aircraft. And then safety culture. So anomaly reporting, if the work is being completed by others, from a culture perspective, why are they not closing the loop? And then, of course, the big one, procedure compliance. So there are some questions there, contextual factors, overtime working, staffing levels, availability of, so to summarise the role of the structure in the accident, the availability of equipment and technical logs, along with unexpected servicing activity, contributed to the technicians completing the tasks on the wrong aircraft. And then just a question, why were the technical logs removed from the aircraft? So we're very near to the end now, and I don't have time to do this, but this is the operations control structure. So this is where we can start talking about the pilots and the way that they do an aircraft walk around. So before you go flying, you are supposed to basically walk around the aircraft and check that it's fit to fly. This is an example of an aircrew bending down to look at these locks. Now obviously, in this case, this particular person was trained in the first week they started with the airline 7 years before. Hey, you might want to do an aircraft walk around, and while you do it, just make sure you check those locks. 7 years later, they don't do it, and we end up with an accident. Fortunately, everybody escaped safely. So final slide, final thoughts. Now this is about near misses. So if you have any near misses or incidents, because we don't have many accidents nowadays to be fair, it's an indication that the control structure is inadequate in some shape or form. And essentially this is a massive learning opportunity. So if you do have a near miss or an incident, it's a cheap learning opportunity because nobody's died and people are more likely to want to talk to you and give you valuable information. So my recommendation is to have a go with cast accident analysis and see where you get to. And that's it. Any questions?
Brilliant. Thank you very much.
Thank you.
Thank you very much.
Cheers.